Hi, class. Today we're going to talk about electromagnetic radiation. It's going to be a little bit different today because you're actually going to take notes on your own piece of notebook paper. So please take out a piece of notebook paper and write these down. Before we talk about objects in space, we have to understand how it is we learn about them. And a lot of the stuff is really far away and we've actually never been to it. The only place we've sent humans to is the moon. And the stuff we're looking at when we talk about stars is outside our solar system. So it's really, really far away. So how exactly do we learn about it? We use something called electromagnetic radiation. And that's essentially the 7 different kinds of light. And it's the only way we're going to see these distant objects unless somehow we invent some science fiction type spacecraft that will allow us to travel these huge distances in our galaxy and in the universe. But until then, we're going to use light, and that's what scientists will use. So make sure that you understand that it's the only way we can learn about distant objects. That's why light's so important. So what exactly is EMR? It stands for electromagnetic radiation. It's the 7 forms of light. You probably have heard about them in some of your other classes. So we're talking about things like microwaves and X-rays and gamma rays and UV and visible light. All of those are types of electromagnetic radiation. Visible is the type that our eyes are adapted to see. We can't see any other types, not infrared, not ultraviolet. There are a lot of animals that can see in some of these other spectra, which is pretty cool, whether it's a honeybee or a snake, something like that. They have the ability to see some other wavelengths that our human eyes aren't adapted to. So anyway, super important here when we talk about this. These objects are so far away, we're not going to be able to travel to them. So the light that travels to us is how we learn about them. It travels at the speed of light. That's 186,000 miles per second. So it can cover long distances in a much faster than we could with a spacecraft or anything like that. So that's how we're going to learn about these really distant objects. So how do we get light? Well, it's formed at the atomic level with movement of electrons from different energy levels orbiting the nucleus of an atom, and that gives off specific photons of light at different wavelengths. And all of these different wavelengths produce different types of electromagnetic radiation. And that has to do with the amount of energy that is released by them. So high energy electromagnetic radiation, a good example of that would be gamma rays are the highest. So their wavelength is very short, lots of energy packed in a very small area. And then the low energy would be like radio waves. They have a very long wavelength, so not a lot of energy packed in the same area. And they tell us different things about stuff in space. So using different types of electromagnetic radiation teaches us different things about objects in space. So let's take a look at the 7 types and what can we see. So each type tells us something different, and you can see the scale on the left going from top to bottom is increasing energy, and going from the bottom to the top is increasing wavelength. And that, because of those different properties, wavelength and energy, that tells us different things about the source that we are looking at. We're going to take a look at 2 sources you're familiar with. The one on the left is the sun. The one on the right is a supernova remnant from when a really big star went and blew up, and this is what's left over. So we're looking at these objects in radio waves, and you can see these images as a result of looking at them in radio waves. They show us different things. So when we look in infrared, we can see on the sun these dark black areas, which must be cooler because infrared is associated with heat. And again, we can see the different types of gases in the supernova remnant on the right. When we get into visible light, those same huge dark areas are small dots on the surface, which we call sunspots. And again, on the right, we're seeing different distributions of gases looking at visible light than we did in microwave, infrared, or radio. When we move to ultraviolet, now we're tipping into the higher energy sources. Visible is kind of in the middle. Radio, infrared, and microwave are low energy, long wavelength. Visible is in the middle, and ultraviolet and on is going to be higher energy and shorter wavelength. So you can see there's something in the middle of the supernova remnant, very, very high energy source in the middle that's producing ultraviolet waves. On our sun, you can see these bright spots, which are caused by ultraviolet waves as well. In the X-ray, we see, again, these bright spots accentuated in the sun, and we see this weird whirlpool swirling thing in the center of this supernova remnant that tells us there is something in there that's high energy that's turning. It turns out to be a neutron star, actually called a pulsar. And then in gamma ray, we don't have any gamma rays coming out of the sun. And on the right, again, in the center of this area, there is a very bright gamma ray source, high energy source, high heat in the center of the supernova remnant. All of these different things tell us different things about these objects that we're looking at and expands our knowledge, because we got to get everything we can from the light that comes from these objects, because that's the only information we have. So in order to see these different types of electromagnetic radiation that our eyes can't see, we use special telescopes and special spacecraft, either in space or on Earth, to look at these objects. And the problem we run into, especially observing from Earth, is our atmosphere blocks a lot of the types of electromagnetic radiation. So gamma rays and X-rays, they don't make it through our atmosphere. Some UV does, and you can tell because you get sunburns, right? Of course, visible light makes it through our atmosphere, and how can you tell? Because you can see. Infrared makes it through. That's how we get some heat, but not all of it does. And then some microwave and almost all of the radio makes it through our atmosphere because the wavelength is so long, it passes through our atmosphere easily. All righty, you have an assignment to do. There are 4 pages in a packet, and you're going to look at some images there and color those images in on your packet, and then try to identify gases of different spectra based on where their absorption or emission lines are in their spectra. Good luck.